Thanks to everybody for organizing B-Sides London. I'm glad to be here to talk to you. And I'm going to be talking a bit about what I do as a security researcher for Tripwire Vert. So this talk is primarily focused around the ideas of being able to do security-focused quality assurance testing. So if you haven't had any exposure into pen testing before and you have a product that you need to start finding vulns in, this is going to give you all of the tools that you need. If you are a pen tester already, it might teach you something you don't know already, but more or less it's approaches to manual fuzz testing to find vulnerabilities. So using these techniques, I found quite a few vulnerabilities. Back in February when I had put these slides together, these were the CVs that I had assigned already this year. Like I said, we're going to be talking about identifying vulnerabilities, the processes that I use, the tools that I use, and I'm going to reinforce this with some hands-on, so some applications which I've identified over time as having various vulnerabilities, and then we'll talk a little bit about what we've talked about. So before you begin any kind of pen test or application pen test, you need to consider what kind of target are we dealing with. If we're dealing with a web application versus an embedded device versus just a raw network protocol, all of these different things are going to have different approaches. And you also have to be considerate of what kind of platforms you're running on top of. So is it Linux, is it Windows, is it running various server-side scripting languages like ASP or PHP, and of course databases underlying different security vulnerabilities and different semantics for your testing. So I've set up what I like to refer to as a security testing tool belt. And in this, we have your hammer, which is your fuzz testing, where you're basically just banging away at something until you get it to break. Static analysis, which is kind of more like your magnifying glass. You're taking a closer look at the binaries themselves, seeing what calls are made in them, what you might be able to find that's unusual. Source review, this is your microscope of your tool belt. This is where you're going to actually look through source code whenever available and look for patterns of vulnerable code that you can inspect further. And of course, firmware analysis, applying mostly towards embedded systems, of course. So to start out by talking about fuzz testing, everybody should more or less be aware of this, but the general idea is that you're going to take some input that is expected for an application. You're going to manipulate that input so that it is not well formed anymore. You're going to execute your target process. You're going to look to see, did it crash? Did it do something else unexpected? Any of those results get recorded, and then you go back into your loop of manipulating the input, running your process, et cetera, et cetera. And then at the end of the day, you hopefully have a nice list of crash dumps and things like that, which you can review for exploitability. So with web vulnerabilities, I'm going to talk about 4 of the primary categories of vulnerabilities, which are very common to find and sometimes very easy to find. First on the list, you've got cross-site scripting. So this, of course, is whenever you have the ability to inject client-side code into a web page so that it's executing in the context of that domain. Gives you access to cookies, things like that. CSRF on the top right here, this is cross-site request forgery. It's when a web application has requests which are ultimately predictable. You're able to actually craft up a web page and make it so that your web page is going to send out messages to another web application. That web application isn't going to be able to distinguish this request coming from your app versus a request coming from a legitimate user because of some things that we'll talk about in how the browser works. Injection, this is a category that covers a lot of different things. So you can have injection of operating system commands, XML injection. Of course, you have SQL injection, LDAP injection, and finally, we'll look a little bit about file inclusion. And so these are vulnerabilities where you can, as an attacker, do something to influence what code is actually going to be loaded on the server side. So back to cross-site scripting. In general, cross-site scripting is going to be a failure to sanitize certain values which get interpreted as HTML. So since you can use HTML to invoke JavaScript contexts, then when this HTML gets rendered by a vulnerable application, content is going to run as if it was legitimate content from that domain. This tends to get introduced when you have things like what we have up here. You have a format string which is being used to create an image tag. If you imagine that that %s is being replaced by the input that I've shown up here on the slide, you end up with an image tag that has an invalid URL and an onError attribute to load some JavaScript. In this case, just an alert pop-up with the message 1. Now, some of the things that we use to look for cross-site scripting are called cross-site scripting locators, naturally enough. With these different formats, they affect different browsers differently. Like, for example, the SVG onload. This I've seen sporadically work in Chrome, pretty much consistently work in Firefox. The image onError tends to work very effectively, although is more commonly filtered by basic cross-site scripting filters. And then the last locator that I have here is one like from the previous slide, where let's say the user has the ability to control the href or the source for some image tag or anchor tag. You can then, if it's not being sanitized, inject a string that's going to include an error handler and launch your XSS payload. So on the bottom line there, that XSS equals alert 1337, you can imagine that's what you would put into all of the locators or something along those lines. Could be alert document.domain or document.cookie. It's just an easy way to recognize that your script is actually executed. With OS injection, this is generally going to be a situation in an application where it needs to be able to run system commands, and it needs to be able to do this based on user input. So the use of eval functions, system functions, any of these that are taking user input without being sanitized, they can all result obviously in unintended code execution. So for example, if you're using the Perl eval command, and you have an eval command that simply takes one of the parameters from your URL, adds some parentheses to make it a function call, you can very easily exploit this by putting in a value with backticks, semicolons, things of that nature, which are going to be expanded by the shell to run some commands in the context of whatever was running this Perl script. So some of the locators that I like to use for doing this, the first one up here is using the pipe command, which of course in Linux is going to take the output of one command, the standard out, and pipe it into standard in of another. So it will trigger command execution if it's not filtered out. You've got another option of using backticks with an echo and then actually providing into that echo valid input. If you run this and it works, then it probably means that either they've got some very nice casting going on that's finding the value that it's supposed to, or you've actually executed that echo command and things are working because you're injecting commands. The last one here, I call this ping injection because you find this on basically every Soho router, anything that's allowing you to do pings or trace routes, stuff like that. In this particular example, you'll see the IP address is invalid. So if that gets passed into ping, it's going to fail. And when it fails, your double pipes are going to say, okay, go ahead and run the other command, uname. So in this case, if you plug this into a vulnerable ping function, the output that you would get would be output indicating the uname from the target system, assuming it's a Unix system or Linux system. Now, with SQL injection, this is going to be, of course, whenever your application needs to be able to access a database, you have the possibility of having SQL injection. This happens if you do not properly sanitize data going into your SQL queries. Common theme coming up here. Not sanitizing input leads to vulnerabilities. And of course, if somebody is able to insert new SQL into your SQL queries that your application is making, they can basically take control of your whole database, especially if you happen to be logged in running the queries as a DBA. So Some of the places where these types of problems come up, of course, again, when you're using format strings, like if you see here, we've got the %s's, that should be an immediate red flag. Of course, it's possible that the inputs to these format strings could have already been sanitized, but more often than not, it's just direct user input. And the proper thing that the developer should have been doing in this case would be to use a parameterized library where you're giving it % and passing to it parameters, and that way you're relying on the library to make sure that nothing unexpected is going to happen. In this example that I've given here, if you plugged in that input for password, the X or X equals X, you're going to be able to log in as any user simply because it's a very, very poorly designed system. Usually passwords, of course, would be hashed, but this is just a basic example. So some of the locators that we use for this, the first one here on our list is the XOR X equals X. The reason that this works is because you're giving it a Boolean alternative. So if there is a check that's saying is username equal to whatever, you're saying is the username equal to whatever, or is X equal to X. And the end quote is, of course, missing because you're assuming that the application is going to fill that back in. Now, with the other examples I have here for locators, first you've got a numeric injection type, and this is ending with comment characters because, of course, you want to nullify the rest of the statement. This can create problems if you're trying to inject into, say, a complex nested SQL query, but more often than not, it's helpful rather than hurtful. And also the having 1 equals 1 is in here because if you're familiar with SQL, you'll see that sometimes this is helpful for being able to get an injection that's going to work later on in a query. So the way that you're using these locators, I felt this needed a special note since I've received a lot of questions about it. Typically, you're going to plug in one of your locators. If you see different results than when you are not having the locator in there, like for example, if you see extra data coming out of something, it's a good indicator that there could be SQL injection. So then the next test that you run is to flip your Boolean logic. So rather than doing X and X equals X, change it to X and X equals Y. And if you're still getting output out, then you had a false positive. But if all of a sudden your output goes away, you just found yourself a SQL injection point. So now we're going to move into the first case study. Is anybody in here, has anybody used ReviewBoard? It's a popular application from which Apache, KDE, various open source projects, as well as corporations like Tripwire and IBM use internally for facilitating the code review process. So I did a little bit of an analysis on this application. I'm going to go through the steps that I used to find flaws in it. So first, the starting point was to scope out what we're looking at. This is a web application. It's Python-based. It runs on a variety of HTTP servers. It runs with a variety of database backends. And from this, we can kind of compile a list of possible vulnerabilities, which I've done so on the right here. So since it's a web app, we're obviously going to look for cross-site scripting, cross-site request forgery. Since it uses databases, we're going to look for some SQL injection. We're also going to look for LFI and RFI. These are your file inclusion vulnerabilities, simply because it's a web app and there's a good chance that you might have some room to get some new code uploaded onto the server. And of course, OS injection is a possibility because this is a web application which integrates with tools like Git and other RCS systems. So there's the possibility that somebody could inject their own commands into that and own your server. So let's start by doing some fuzzing on this. The first thing that you see when you log into ReviewBoard is that, at least under the default configuration, it's set up so that if you don't have an account, you can create an account. So that's what we're going to go ahead and do. And in the account creation field, you can see here that I've entered my name and a username and a password, But for my real last name, I've got this SVG onload tag, which is one of the cross-site scripting locators that we talked about a little bit earlier. And so right away, by browsing through the web interface for this tool, I found that when you go to the submitters list, it presents that full user's name without sanitization. So you can see our pop-up 1337. Yes, you can read it on the slides. That's good. And then again, I found that when you go and you want to assign a review to somebody, you start typing in their name, it has a nice little autocomplete widget. This autocomplete widget, of course, renders the name without sanitization again. So you get a pop-up. So these were two CVs that were assigned. The first one, of course, the submitters list not being sanitized, the autocomplete not being sanitized. And Christian Hammond of the ReviewBoard project was very good about implementing a fix wherein their underlying library would now sanitize everything globally. So realistically, there shouldn't be cross-site scripting vulnerabilities left. So then, if we talk about what kind of risks there are from not updating this, or if you wanted to, say, show to your management or in a professional engagement, show to your customer that there are actual serious risks as a result of these cross-site scripting vulnerabilities being unpatched, you can spark up Kali Linux, load up Backtrack, or load Beef rather, or you can load Beef on any other box. And this is an excellent tool for just gives you a little script that you can use in your cross-site scripting payload. And then you can't really see it here so clearly, but there's a little screenshot showing what it looks like when you've put something on your meat hook in Beef. And from there, you can do things like injecting Metasploit exploits into a page. You can start enumerating cookies, look through what sites have been visited on the browser. There's even the ability to do limited keystroke logging through it. So what this all teaches us, as developers, we have to be expecting the unexpected. You can have situations where you're going to trust output because it's coming from a system caller. It's already in your database. But really, you need to think about, has this data been sanitized somewhere before you're getting, and if the answer to that is no, you treat it as tainted and you sanitize it. So when I looked at IBM WebSphere last year sometime, I found that they were not doing this. So system calls for enumerating the file system. Of course, under Unix, you can have file names which have greater than and less than tags. These can be used for cross-site or for HTML attributes, HTML tags. And in the WebSphere administrative console, they have actually a little file browser where you can go through and you can see what files are on your server. Now, if somebody happened to be able to create files on your server with special file names, when the administrator goes to browse that, they're going to have a cross-site scripting payload run. This is actually a really common mistake. I've seen this on more than one Google service. It's paid out a bounty. I went back to ReviewBoard, and I looked at ReviewBoard considering whether or not they might have the same type of problem. So the text is kind of small up there, but you can see I'm uploading an attachment to a review, which has a name that's a cross-site scripting locator, and the actual file name itself is a cross-site scripting locator with a .php extension. So upon uploading it, we see that this was properly sanitized. That's the output, something like the output that you would want to see. You don't have a pop-up. You see &LT, although that's a little weird. You should probably see angle brackets. And the file name itself has been sanitized in such a way that we have underscores instead of spaces, and our carets are completely gone. But when we actually click that file, we have a web shell. So this is a file inclusion or remote code execution vulnerability. There's a bit of stuff that we could do. From this console, an attacker would be able to start running commands on your server, browsing files, creating connect-back shells, things of that nature. So this vulnerability stems from the fact that ReviewBoard gets installed by their install process. their install process sets up uploads directories, and it doesn't bother to actually, or didn't bother to actually set up permissions on these upload directories to prevent things like PHP handlers or other kind of server handlers from running there. So also you could very easily upload HTML documents regardless of what kind of handlers are installed on the server, and you have perfect ammunition for cross-site scripting attacks, phishing attacks to try and gain credentials. And of course, like I showed, if there is a PHP handler or mod ASP or something like that, you would be able to get a web shell on the server. And this is a problem that just updating ReviewBoard doesn't do anything to fix it. Updating ReviewBoard and then reinstalling your site or reconfiguring your site is the only way that you could eliminate this flaw. And they did that through adding specific content handlers and removing unnecessary content handlers, or recommending that you use a content delivery network. So we just talked about all this. I'm not going to say that again. But let's move on to wireless IP cameras. Has anybody in here considered or used a wireless IP camera for home or office security? Few hands. So I myself, I had the same desire. I go on a lot of trips, so I wanted to be able to monitor my home remotely. So I bought a camera that looks kind of like that one on the top right there. And I thought, oh yay, I'm going to be able to put this in my DMZ, access it from wherever I want. I don't have to bother going through my VPN. And before I did that, I decided, all right, we'll spend 15 minutes doing a security review. So first thing we see when we look at this, it's got an HTTP interface for both managing the device and viewing the camera feeds. And on this HTTP interface, it's got a banner that I had never seen before. The banner was NetWave IP camera. And throwing some basic options verbs at it and things like that, doesn't seem to be like a fork of Apache or anything well known. So there's a good chance that it's a custom IP implementation. I found out later it came from OpenIPCam. So I decided that this would be the ripest target to look at, that if it's a custom HTTP implementation, there's a good chance they made mistakes that people before them have made. There's also the very much likelihood that the web interface is going to have vulnerabilities because, well, most web interfaces have vulnerabilities. So we'll start looking for low-hanging fruit. This is the management page. I've got the Chrome developer tools loaded on the bottom. You can kind of read it here, but this is the list of users configured on the device. Let's go ahead and send that request, and then in the Chrome development tools, look at the request that came across. Now, what you can see up here is that this is a GET request, and it's a GET request that has in the URL parameters a list of every username, every password, every privilege, and what's missing is a nonce value. So what happens if we have a web page that has an image tag on it, and that image tag has the source referring to the IP address of your IP camera and that set user's CGI script with some parameters being selected to change your passwords? Well, the browser is going to request the URL. If your browser knows credentials for the site, it's going to automatically push those credentials out, and the camera is going to treat this as an authenticated request, as if you, the legitimate user, had gone in to change your username and password or add a new account. And so the fixes for this type of problem, primarily you don't ever want to be able to change passwords without entering a password again, forcing reauthentication. And most importantly, these types of requests should be treated with a nonce value. The reason for this is that if you have some unique value coming out in your page, and submissions to that script are going to require that unique value to match, you're not going to be able to do cross-site request forgery without violating the same origin policy, because you're going to be able to send requests, you're not going to be able to read the responses unless you have some special situations. So this is get-based CSRF, very trivial to exploit. And even if you had, say, some trusted websites that could be tricked into hosting an advertisement with the crafted URL, or forum pages with crafted URLs, you could start exploiting this on a massive scale. But this was the least of the problems with this device. The next thing that I decided to look at was directory traversal. And this is a bug straight out of the 90s, and so I was really, really very surprised and disappointed that the camera that I just bought in 2013 would have this problem, but lo and behold, doing a curl for /./etsyresolve.conf shows me name server configuration from it. So that's bad, but let's see if it gets a little worse. So when we put all the pieces together here, we can see, first of all, there's resolve.conf on the system. If resolve.conf is on the system, then most likely this is a Linux or Unix box. We're going to guess that it's probably a Linux box. And in Linux, we have the proc file system. A lot of times the proc file system is configured with mounts for mem, kmem, whatever, that are going to give you access to the system's memory. And in that memory, you have passwords, not just the password for logging into the system, but also passwords for everything else that it's going to use. So SMTP servers, DNS servers, FTP servers that you want to load images to. So I wrote a little script. There's a screenshot here just showing how easily you could parse out the recognizable pattern of the admin username and password. This is, of course, actually the default credentials on the box, but works just the same. If you change the username and/or password, you can look for things in memory that are going to precede this and easily identify that data. So, like I said, you have the admin password being disclosed this way. Any other services, which are authenticated services configured on the box, their passwords are going to be disclosed. So for example, my Comcast mail password, which was necessary for having the camera send out alerts to me during movement, that would get disclosed to anybody who knew the IP address of my camera without having knowledge of the password and in a straightforward and automated fashion. And also, of course, you could probably DOS the device just by repeatedly requesting a dump of the memory on it. It's not going to last very long. So this gives a decent segue into firmware analysis. In that particular case of the camera, I didn't do any firmware analysis because the only way to get the firmware for it at that time would have been to get it off of the chip. There were no released firmware updates for it. They have since given me a firmware update that they didn't post on the website for some reason. But nonetheless, with other devices, it's very helpful to take a firmware update, like say for your D-Link or Netgear router. And Craig Hefner has a great tool out there called Firmware Mod Kit. This will allow you to, it uses binwalk and walks through the file system for the update, or for the file for the update, looks for known file systems, extracts them, mounts them, and all of the data that you get out of this, you can use for static analysis, and you can also use some information from it to find backdoors. Like for example, there have been cases where we've seen hard-coded user agent strings within HTTP binaries, which allow you to bypass authentication, and other similar vulnerabilities, which I'll get to in a moment. So jumping ahead a bit, because I want to kind of intermix these two topics, static analysis is, at least from my perspective, the analysis of binaries without actually running them. So this gives you a way to analyze potentially malicious code. It also prevents the process that you're examining from recognizing that you're examining it. And there's lots of great tools out there for doing this, free tools. You've got objdump, you've got strings, binwalk. On the commercial side of things, IDA is a great tool. They also have a free version, which is kind of old, but still quite helpful. Now, if we combine the static analysis approach and the dynamic analysis approach, we can get some interesting power out of our firmware analysis. So first we can say extract the firmware from a router. When we extract the firmware from the router and mount the file systems that it has, we can actually see all of the files which are going to be in the public HTML directory for the web server. Adding on to that, we have binaries on the system, like the HTTP daemon. We can dump strings out of that or do an obj dump of that, and we can start to look for patterns of other things that look like they could be URLs or URIs buried within the code. Once that's found, we can prepare a list, and then having the device online and accessible, we can iterate through this list and request every possible page that we think is on the device or handled internally through the web server, and then keep notes of what data is being returned from each of them, what return codes are coming out, and what kind of sensitive data is in there. So doing this approach on Soho routers, we found that 37 of the top 50 routers on Amazon, we, by the way, did not look at all 50 of the routers, so it's quite possible that 50 out of 50 of them are having critical vulnerabilities, but from the ones that we had available to us, there were vulnerabilities which were quite critical, which were present on 37 of these top selling ones in the US. So I'm going to do a little bit of a demonstration of some of the stuff that we found with this approach, but because all of the routers are basically crap, I'm just going to, I've made a little masking proxy which does not reveal the strings that are being used to bypass authentication here. You can Google around for it, you'll probably find it, but you should just kind of think about this router as being every router, because they're all about equally as vulnerable. So on the top here, you can see when we request the page directly, we get an unauthorized message. It's saying that you need credentials. On the bottom, I've instead requested the page with this question mark replaced with magic, which my proxy string behind the scenes is replacing that with some set of characters which I found to be common amongst all of the file or all of the server resources which were given to me without authentication. And when I make this request, you can see that one part of the page, this little nav bar on the side, is actually being displayed. And so that tells us that at least one of the requests was authenticated or was treated without needing authentication. Taking this a little bit further, if we do a request directly to the backup CGI script on the device, we can download the configuration for the router without having authentication. This configuration file, of course, contains passwords for any services that are configured on it, and of course the router administrative password. So you basically own the box without too much effort. So what we did here, we assessed what files are actually on the device. We went through and we attempted to access each of the devices, each of the files, and what we came up with was a list of files that all were acceptable with 200 OK and some content potentially. And then by looking across all of these URIs that are being accepted, patterns emerge. And using those patterns, we're able to see, all right, well, when our request ends with such and such, we're going to bypass the authentication checks. And then after this was determined, I opened up IDA and obj dump and started looking through the binary and realized, yeah, there's a check in here that's saying, all right, if you see certain file types, you're going to treat them as not needing authentication because, of course, there are some things that you need to be able to access on the system, like that unauth page that was up before, which are going to need to be accessible without a username and password. And that's essentially the root of this vulnerability, that and the fact that they didn't actually enforce that the file name that they were grabbing was having this extension, but rather just that the URL coming in ended with this extension. So question marks could be used to fool it. So what you could do with this vulnerability, really the things that we've seen with like the Moonworm and other vulnerability or other worms attacking routers and other mass attacks against routers, people are changing DNS settings so that they can start hijacking sessions. You can actually upload a completely new firmware to the device, which is going to prevent it from receiving future updates or giving any indication that it's been compromised. And of course, anything which initially would have been an authenticated vulnerability, this is now exposed to you because you can bypass the authentication. So some of the other things that came to light during this process, we found that error pages on one brand router in particular had a huge flaw in them, in which there was client-side code that was being used to determine whether or not the system was in a first-time setup mode. So the JavaScript would actually come out saying, all right, if admin equals, and then the server would replace the other part of the expression with the actual configured password, then you're going to redirect to one page, otherwise you're going to do something else. That something else is irrelevant because now you have the password. And also a bunch of other things like IP addresses and MAC addresses from the internal network get revealed, a lot of debugging information which would help you if you wanted to be able to, in an automated fashion, identify a router and determine what vulnerabilities you know about in it. So looking at source code review, the general idea here is that you're going to be looking for patterns within the code that are indicative of security failings. So for example, the traditional memory corruption vulnerabilities came from sprintf, stircat, strcpy, things like that. SQL injection, if you want to find this in a code base, just start looking for places where you see different SQL verbs and perhaps augment that with looking for format string specifiers. When you find these are particularly suspicious and should have a second look at seeing whether or not they're exploitable. And of course, for OS injection, depending on what language you're looking at, there are a number of functions which you should be looking for usage in your code and verifying that it's being used safely. So some tools for doing your source code review. We've got grep, of course. The OS project has their Labs tool, which is more specific for web applications. And Google is an excellent resource. The Google code search capabilities have turned up some vulnerabilities in the past. So this is a piece of source code. It's kind of C code. Can anybody read it? Can anybody see what's wrong with this? Any hands? What's wrong? Yeah, so no buffer overflow here. Well, it's an snprintf, so if you've got data being longer than buff, it's not going to overflow anything. It's only going to write the size of buff into there. Any other guesses?
It doesn't skip the null time later? Doesn't put the null time later if it's the same language?
Yeah, there could be something with that. That's not actually the particular vulnerability that I've found in this. So let me go ahead here. This is actually a buffer overread. In this situation, snprintf, if you have data that is longer than the size of that buffer that you're putting it into, snprintf isn't going to return the number of bytes which were actually written into the buffer, but rather the number of bytes that would have been written into the buffer had it not been a bounded string function. So on the next line, when you go ahead and do a send, and you're using the return value from snprintf, this len, you're going to end up sending more data than you expected to. You're going to read off the end of the buffer because len can be considerably larger than size of buff. So properly written, this code should only be sending at most size of buff. So it should be size of buff with the ternary operator, and if size of buff is going to be less than the len value, you only want to send size of buff bytes. So what is a buffer overread? Why is it important? So this is CWE 126. In general, it's whenever you're using a buffer and you're not paying attention to how long this buffer is and getting data beyond the edge of the buffer. And there's obvious reasons why you should care. In case you hadn't noticed, this month, basically the internet got turned upside on its head because of a buffer overread vulnerability in OpenSSL that we call Heartbleed. So it should be pretty clear why buffer overreads are important to understand. Now, looking at MiniUPnPd, I found back some time ago a buffer overread. This is a buffer overread in a network service because, like that code sample that I had up on the screen there, they were using the return value from snprintf and weren't considering the possibility that that length could exceed the size of their buffer. And so if you would send a crafted UPnP message, you could cause a send that's going to come out and send you extra data from the heap. And that extra data in the heap is going to be UPnP messages. So you could actually use this from outside of a network to start fingerprinting and seeing what's inside the network. What packets has this UPnP daemon been receiving? And from there say, okay, I know there's a NAS server or a media player or whatever else that might be using UPnPd on the inside of this network that I'm only on the outside of, and I can get version information about it and use that in reconnaissance for a future attack. Now, there are other instances where you also have to worry about the use of snprintf and other bounded string functions, which are supposed to be safe. So ReadyDLNA, another media-related product from a Netgear developer, they had fixed up some stack buffer overflows which had been publicized and replaced them with a heap buffer overflow. The reason that this happened is because they were using signed integers to calculate length fields. Never use a signed integer to calculate a length field. There's no reason that your length is ever going to be negative. So in this particular case, the user could send data which is going to make this signed buffer or signed integer roll over, and you're going to have unexpected results. And you can actually corrupt the heap this way. And although it would take a bit of work in this particular context to get code execution, at a bare minimum, you have a denial of service attack from this. So, in summary, you've got vulnerabilities everywhere. All of the systems that we deal with are vulnerable in different ways, and when you start to train yourself to be able to look for these vulnerabilities, you're going to find them, and you're going to find lots of them. And what I've found is that you can run a lot of animated or automated scanning tools, and they're not going to find things as quickly as just one or two QA people going through and manually putting in different vulnerability locators into every field of your application. So I also want to mention you shouldn't be using any of these tactics or techniques on systems that you don't own or don't have a professional engagement to be testing. You want to be careful about what you're disclosing. If you're going to disclose something publicly, you have to understand that it can put a lot of people at risk. So be patient with the vendors. They're not necessarily going to be as smart as you when it comes to security, and they might need a little bit of hand-holding in order to figure out how to properly remediate the vulnerability. So I spend a lot of my time going back and forth with vendors and explaining to them why particular fixes are incomplete or what the proper way of doing things is. So since I still have some people here, we're going to go back to the router because I like to end presentations with more than just a little summary. So I had mentioned that with the authentication bypass on the router we looked at earlier, it exposes also vulnerabilities which generally would only be exposed to an authenticated user. Now, this is one such vulnerability. You can see, this is the ping 6 functionality of the router. And if you give it an IP address that has backticks in it, it's not going to do anything to take those out before it passes it on to the system call. And so when we run backtick echo and then the loopback address for IPv6, you end up getting output that looks like it's pinging the loopback address. And so it's a good indication that there's command injection. I actually verified this by doing some other things, like since we have the analysis of the firmware, we know the file system layout, I could issue an ls/bin and send that output to a file in the web sharing directory. And then when we go back and browse to that file, we're going to have output from our commands. And then, of course, on the bottom line, we have a semicolon utelnet d-p1337. Any guesses what that's going to do? So what we've done here, we extracted the firmware. We found that there was a hidden ping page on there. We fuzzed the parameters very briefly. The way that I actually tested it the first time was just by doing backtick reboot, backtick, and found, yep, box reboots. And it's a very common problem. Like I said, even some routers you will find that you can trigger, like on some of the older Linksys routers, you can trigger the ping functionality with an injection without having any authentication. Just a post request to the script and it will ignore whatever credentials are sent. So it's a pretty serious problem, something that could be very easily put into a worm to propagate. So, of course, this is what you get when you actually would run that utelnet command there. We've opened up a shell on port 1337, and when we connect to it, we can see that the router under the covers was using OpenWRT, and we have a root shell. And of course, we have a root shell because, as shown by PS, you have the web server running as root, because who wouldn't want to run their web server as root? So here's some of the tools that I talked about. Lots of good ones in there. Does anybody have any questions? All right, thank you guys for your time.